Hey guys, this last lesson, Unit 4, Section 4, is going to be kind of a blast from the past because we're going to be using a lot of theorems that we learned in Chapter 1. So it's been a little while since we've used them. Hopefully they'll come back pretty quickly. But we are going to be working with coordinate proofs. So we're going to be proving that figures are parallelograms using the same ideas that we talked about in the previous video. So any of those 6, but we're going to be doing it on a coordinate proof. Some of these are easier to do than others on a coordinate proof. Okay? When we're talking about angles, angles are hard to do. And in fact, we can't really prove that angles are supplementary without like a protractor on a coordinate grid, so we're not going to be doing that one ever. The ones that we're going to mainly be focusing on is proving opposite sides are parallel, congruent, or that the diagonals bisect each other. And that one is actually the easiest, is to prove that diagonals bisect each other. So I will start with that one. Here are some of the formulas that we use: slope, distance, and midpoint. Remember that slope proves that things can be parallel because if you have the same slope between two lines, then they have to be parallel. The distance formula would give us the lengths of sides, so if we could use the distance formula to find that opposite side lengths are congruent, that would help us. And then the midpoint formula actually shows us where the midpoint is of a segment, and this has to do with the diagonals. So I'll talk about this here in just a second. Every single time you have a problem like this, it's going to say plot these given points and then establish, prove, justify that ABCD is a parallelogram using those 1 of 6 shortcuts. So let's go ahead and plot these. Remember, it's X and Y. So -2 goes back 2, down 3. 0, 5 is 0, up 5. 6, 5 is over 6, up 5. And then D, 4, -3 is down, or over 4, 1, 2, 3, 4, down 1, 2, 3. Okay. Now, this one, what I would suggest doing is first connect your points. Recognize the fact that we can actually count out the points on the top and the bottom. This definitely looks like a parallelogram. It looks like opposite sides are going to be congruent, opposite angles congruent, looks like they're going to be parallel, all of that. But we have to justify using math, the formulas, to give us some concrete evidence that this truly is a parallelogram. What I would recommend for this one is to prove that opposite sides are congruent. The way that we're going to do that is you can actually just count the distance on the top and the bottom. Since the y value is the same, we're just counting from left to right. So 1, 2, 3, 4, 5, 6 units. We don't have to use the distance formula for that because it's a linear distance. It's going straight across. So that's going to be 6 units. You don't have to write the units part, but. And then the bottom, same idea. 1, 2, 3, 4, 5, 6. We can just count that. But now this distance here and this distance here, we can't just count over by units because it's a diagonal distance. So it's not it's not the same idea as counting from this point here, which I should have labeled. You should always label your points here too. Let me fix that really quick. So this was A, B, C, D. The distance from A to B and the distance from D to C, that goes at a diagonal. So we have to use the distance formula for that one. So let's do that. A and B are these points here. So this is going to be our x1, y1. This is going to be our x2, y2. The distance formula is up top. This formula right here is the one we're going to use. So it's the change in your x's plus the change in your y's. You square those and then take the square root. So if we plug that into our formula, D equals, we're starting with A and B, so x2, x1 is 0 minus -2 squared plus 5 minus -3 squared. Okay, we get the square root. 2 negatives makes a positive, so this ends up being 2 squared, which is 4, And then these also end up adding, so it ends up being plus 3. 5 plus 3 is 8, and 8 squared is 64. We end up getting the square root of 68. So for right now, we're just going to leave our distance as the square root of 68. That's enough for right there. Now we got to do the same thing, but we're going to use D and C now, the other side. We want to prove that that's also the square root of 68. So this becomes our new x1, y1, x2, y2. D equals the square root of x2 is 4, x1 is 6, plus, and then we use y2 is negative 3, minus 5 squared, and then we will do this. 4 minus 6 is negative 2, negative 2 squared. Negative 3 minus 5 is negative 8. We got to square those. We get 4 plus 8 squared is, negative 8 squared is 64. So we do end up getting the square root of 68 again. Since we got square root of 68, that tells us that those pairs of opposite sides are congruent. Therefore, since both sets of opposite sides are congruent, it has to be a parallelogram. We're just going to write down here both pairs of opposite sides are congruent. That's enough to justify that it has to be a parallelogram. And you showed your work, so that's kind of like your evidence. The statements are the square root of, or AB is congruent to CD. That's the idea of a normal proof. This is just more of the mathematical side of proving that they're congruent. It's less to do with like the words and the well, there is justification. It's just with numbers rather than words. Okay, so let's go ahead and try this next one. Plot ABCD on the grid, just like we did before. And I'm going to show you another method that we can do for this. So negative 3, negative 4 is back 3, down 1, 2, 3, 4. Negative 1, 2, and that's our A. Back 1 up 2. It's B. 7, 0 is over 7. 0 like that. C. And then 5, negative 6 is way down here. And that is D. Now we connect our points. For this one, it's a little bit harder to use the distance formula because we don't have any of those straight across distances. Nothing's up and down or left and right of each other. So we would have to use the distance formula 4 times. That's a lot of work. Another way, my favorite way to do these, is to find the midpoint of the diagonals. The way that this works is if the midpoint is the same for both diagonals, you know that they have to meet at the same spot, and therefore they bisect each other. Okay? So we want to find where the midpoint of the first diagonal, AC, and the midpoint of BDR, and we want to justify it mathematically. And we can do that because we have the midpoint formula. Again, this is the one I recommend the most just because it's most convenient and everybody likes the midpoint. You're just adding up your x's dividing by 2, adding up your y's dividing by 2, and that's how you find it. Okay, so the first one here. We want to start with A and C. So this is going to be our x1, y1. This is going to be our x2, y2. So the midpoint is going to be the average of the x's, negative 3 plus 7 divided by 2, and the average of the y's, negative 4 plus 0 divided by 2. Negative 3 plus 7 is 4 over 2. Negative 4 plus 0 is negative 4 over 2. And that equals 4 divided by 2 is 2. Negative 4 divided by 2 is negative 2. So there's one midpoint, so which is this right here. We're really close to where we marked. Now I'm going to erase these and do the same thing, but this is going to be my new x1, y1, and this is going to be my new x2, y2, because we're using the other diagonal this time. between B and D. X1 is going to be -1 plus 5 over 2. The other one is going to be 2 plus -6 over 2. Again, we're hoping that 2, -2 is our second midpoint. So we get -1 plus 5 is 4 over 2. 2 plus -6 is -4 over 2. And I hope you're silently cheering because 4 over 2 is 2 and -4 over 2 is -2. So we get the exact same midpoint between the diagonals. Again, this is great because it tells us that the midpoints meet at their middle. Therefore, this is congruent to this, and this is congruent to this. And diagonals bisect each other. That's what it proves. So we can say ABCD, I should have said this earlier in the first one, is a parallelogram. We can write out a sentence. Because the diagonals bisect each other. All right, and that is it for this lesson. We'll do some more practice with these in class as well.